Section 6.52. Now we're going to do an example on second partial derivatives. Partial derivatives tend to have a lot of symbols. Second partial derivatives have even more symbols. So the total amount of algebra you're going to do is going to escalate. But other than the huge amount of work, the problems themselves are never really that hard, as long as you do not make a mistake out of the huge amount of work that you're going to be cranking out. So let's look at this example, which says u is a function of u is equal to f of r, a function of r, and we will represent r as commonly represented the length of the vector x squared plus y squared plus z squared over n square root. Now we want to show this particular relationship. The purpose of showing a relationship like this, one way is that if you can show that equal to that, it is also a way that you can actually do this as a differential equation and actually figure out what u have to be. Say if this thing equal to, let's say a number such as 0, then once you know this equal to 0, you can solve for u, and then that will be easier to solve, say, directly from here, because now then you have only one variable instead of 3 variables. So let's see how we're going to go about that. Well, you go about it the old-fashioned way. That is, you crank it one step at a time. First, given that u equals f of r, partial u partial x equals to, okay, it's just, let's write it down the principle first, because whenever you have a whole load of symbols, it's very, very easy to get confused. So f has only one variable, so it equals to df by dr times partial r by partial x. Because f has only one function, so we don't do the partial, we just take the direct derivative. Whereas r is actually a function of 3 variables, so we'll take the partial. Now, what is that? Let's calculate it. So that equals to, we'll call it f prime. F prime is just df dr. And being the f is u, that's the same as du dr, but we'll worry about that in a second. So that equals f prime partial r partial x, okay, right here. Take derivative with respect to x, which is, we'll take that, is 1/2 times 1/2, okay, that's coefficient. And then 1 over r, we'll just write down r instead of the whole thing, this thing on the denominator, and then 2x, which is just equal to f prime times x over r. So that is one thing. And then the next thing will come much easier. Now, what is partial u partial y? This, now, when you do y instead of x, being that everything is completely symmetrical, everything will come out exactly the same. So it will just end up being the same thing as here, except the x is now y. So it equals to f prime times y over r. And here, remember, what is f prime? F prime is the derivative of f with respect to r. And that is, f prime is the same as du by dr. And du by dr is what we are trying to drive at some point. But for now, we'll just write it this way. And then the third one, partial u, partial c, same thing. Is going to be f prime z over r. All right. And now, okay, that's just the first derivatives. We are striving for the second derivatives. So now we're going to take the derivative of all this stuff and crank it again. So next step, partial squared u by partial x squared is, now this is, this relationship right here, remember this is multiplying. It's not some other odd thing. Okay, this is all multiplying. So if you multiply, then we use the product rule in taking derivatives, which will come up to be the first, take the derivative of the second, which is just 1 over r, okay, plus the second term takes the derivative of the first. The second term is x over r times the derivative of the first. What is the derivative of the first? Well, the derivative of the first is f double prime, and then take the derivative of the r. In effect, you're doing the exact same thing as here. That is, instead of f, now it becomes f prime. So then the whole result come out to be exactly the same. And all you have is f double prime x over r. Or you can just work it out. It's the same. The point is that you take the derivative of f prime, and then you end up with something like this. And then the next thing is partial squared u partial y squared. And that would be exactly the same because you're just doing it with y, but the equation is symmetrical all around. So everything is exactly the same, plus y over r, as is shown here, times f double prime, and then this is y over r. And then it's the same way with the third term, partial squared partial u partial c squared is f prime 1 over r and plus y f double prime. Now this you have c. Okay. Now and remember that f prime is du by dr, and f double prime is the second derivative, so it's the d squared u by dr squared. And the reason we say f instead of all the stuff is just to save on some writing, which helps, but then you also have to remember what you're talking about. So this is what we're talking about. And at this point, we will do a total because we're trying to show the summation of all this stuff. So what does the total add up to be? The total is going to be 3 of these things. So 3f prime over r. Okay, plus this is x squared, y squared, c squared. So its total is x squared plus y squared plus c squared over r squared times f double prime. All right, and that equals to 3 over r. Remember what f prime is. It's our short form for du dr. Plus, this is 1 because r squared is the sum of x, y, and c squared, okay, as shown over there. So this is just 1, and then this becomes f double prime, which is d squared u dr squared. And that is exactly what we were trying to prove from the very beginning. And this is actually a fairly easy problem, as you notice that things didn't go out of hand. And everything kind of cleaned up very nicely because of this division here. Now, if you were to be asked, let's say this number is 0, and how would you solve for u? If this is given a value, in other words, you're doing a differential equation, then you can solve for u by, well, whatever differential equation tricks that you can come up with. Then you can very soon you can work it out that this is happen to be an easy case, that du by dr equals to a constant over x cubed, pardon me, a constant over r cubed. And therefore, and then you do the differential equation again, and then u then equal to c over r squared plus d, where c and d are just constants. Or you can write it a different way, where r squared is represented by the sum of x, y, and c squared. So then the whole function will come out that way, if you were to solve for this thing equal to 0. And that's one nice clean example of partial differential equations. And most of the time it doesn't come out that fast, but it does always come out if you go through the whole thing and keep your mind clear.